Okay, so the first thing I want to say on here, since we have a test on Monday, step one is get out your cell phones that I just told you to put away. Get them out and go to your calendar. And on your calendar, go to Saturday or Sunday, whatever day you think is going to be better to watch these videos and review. This is the Unit 1 test. It's going to be worth more points than your quizzes. Probably twice as much, 2 to 3 times as much. I got to look at how many points I'm making it. It's going to be worth a lot of points. And as I just told you, there are several students that are turning in their assignments. They're doing what they're supposed to do. The assignments might have some wrong answers here or there. We go over them on these videos. But what's killing people is the assessment grade. Part of that, by the way, is that the mass and volume lab did count as assessment points, 10 of them. So if you didn't turn that in, make sure you do. And other than that, we got to do better on these quizzes and tests. You guys, when I talk to you and we're working in groups and stuff, it seems like you understand concepts, but when it comes to actually showing it on a quiz day, that's the modeling stuff, sometimes we come up short. So make sure you watch both videos. There was a video I posted yesterday where I went over the answers to part 1 and then part 2. Also on Monday, you should have somewhere some mass and volume notes. I know some people accidentally turn them in early, but those are actually due on Monday before the test, and that will be homework points, but I usually make them worth quite a bit. So make sure you turn those in on Monday before the test, have those with you. That's that density concept. And so with this modeling, you guys got to understand, you got to be able to show me that you understand the conservation of mass idea. You got to show me that you understand the concept of density through modeling. You got to show me that you understand the concept of physical and chemical changes. And again, that goes along with conservation of mass. Got to be able to show it. So I'm going to try to get all that in this video as I go through the answers. So number 20, we did 1 through 19 on part 1. 20 is burning a piece of wood, a physical or chemical change. Chemical. Okay. Now, provide evidence. Now, one thing we can look at, this is not always the case, but a lot of the time, if we see a change in mass, that could be an indicator that it's chemical. Although we could have physical, like where we boil something, and that would be a change in mass, but that's just a physical change. But a lot of times we see that change in mass. It kind of indicates chemical. We might be thinking chemical. But here's how we check for sure. I gave you 4 pieces of evidence that we use for chemical changes have occurred. Release energy. So was there a sound? Was there an explosion? Do we see flames? Feel heat? Any of that stuff? Release of energy. And that one would apply to this scenario here because we're burning a piece of wood. All right. Another thing, is there a color change? There is a color change. So that wood is going to get dark. It's going to turn black or gray, right? It's going to turn to ash. The color change, not like just painting something or putting dye in water, food coloring in water. That's not going to be a chemical change. That's just physical. But another thing is, do we see gas produced? Gas bubbles. That's an indicator of a chemical change. And the last one we had was formation of a precipitate. So we had a couple of liquids we combined, and then it got super cloudy. And that's because it was forming a precipitate inside. If we gave it time, that precipitate would have settled to the bottom. That's a solid, all right? When we did the, what was it, sodium nitrate and calcium, I forget what we used now. But that was the last station. All right, so that's all number 20. What about number 21? You pump air into your volleyball ball. Volleyball. You pump air into your volleyball. What would happen to the mass of the volleyball? It stays the same? It increases. Why would it increase? Really, when we're putting air in, we're adding air particles. Do air particles have mass? They sure do. Do they have a lot of mass? No, not really. So when you pump a volleyball full of air, yes, you are adding mass. Is it noticeable? Not really. But if you took that volleyball and you put it on the balance to find mass, and then you pumped air into it, you would find out that the pumped up volleyball has more mass than the flat one. All right? A piece of butter melts. So really what we're saying here is we're just melting the butter. We're not like cooking it and changing things. If it's just something just melting, the particles are just changing their arrangement. None of the particles are leaving the system. There aren't going to be any particles entering the system. The butter is just melting. Butter would be the system there, yes. All right, so it just stays the same. Number 23, the mass of a rusty bicycle is found to be slightly greater than the mass of the same bicycle before it rusted. The change in mass indicates that the rusting process change in mass, I'm going to think chemical change. And since the mass went up, I would say particles must have entered the system. And I lost my train of thought earlier. I was telling you about your cell phones. You need to go to whatever day this weekend you think you're going to have more time. And you can do this right now. Go to that day on the calendar, put in an event, study for chemistry, watch videos, whatever you want to put. Whatever time you think you're going to get up. You guys get up at 5:30 on the weekends like I do. So maybe you get up at 10 o'clock or something. Set an alarm, put the event in for that time. Make sure you have an alert. Make sure you get a notification because you will forget to study for Monday's test. I guarantee it. So make sure you have that in your calendar. Okay, so moving on now, 24, A, B, and C. And I'm going to use specific examples from quiz 3 since I'm not making a video to go over that on before Monday. So some examples from the mass change lab that we did. So first of all, I got to understand that if we get an increase in mass, particles must have entered. Okay, particles entered. So I'm going to do a before and after. This is going to be my before. This is going to be after. Now, this was one of the questions on the Unit 1 Quiz 3 that a lot of people missed. 90% of students missed. Probably because when I'm talking about it right now, people have their heads down in their desk or they're looking at their cell phones or something like that that they should not be doing because they should be paying attention going, what is he talking about? What's he trying to teach me right now? So the one where particles entered, the only station where we really should have truly seen a slight gain in mass, which is what that data showed on your Unit 1 Quiz 3. I showed you sample data, and there were like 3 groups that showed no change, and then I had the other 4 groups showed a slight gain in mass. You know that a lot of the stations, either the mass stayed the same, or more commonly probably lost particles, lost mass. Like even the steel wool pull apart, it should have stayed the same because all we're doing is pulling it apart, but some of the steel wool stuck to our fingers, and so we lost a little mass. But steel wool burning is the one that we should have had a slight gain. Okay. Because when we burn something, we're going to use oxygen. So maybe I make a couple dots of oxygen in the air. Okay, so I got to make a key. Blue dots, O2. And of course, I had the steel wool. Maybe I'll just make a box for that. And maybe I'll make 3 dots of that. And if you don't know what's in steel wool, just make black dot SW particles. Those should say particles. All right. And then in the last picture, I'll draw that steel wool again. And I'll still draw those 3 dots in there. But now maybe what I'll do is I'll combine the blue dots with them a little bit. Okay. And I'd probably put an explanation on there about what I'm showing if I had more room, which I don't. But this is how we demonstrate, first of all, think about it. When we find the mass of the steel wool, it has a mass of 3 particles. When I find the mass afterwards, the mass increased, according to my model, increased to 5 particles. But what this also demonstrates in this model is that I understand the law of conservation of mass. Because overall, I'll put these in green, overall I have 5 total particles in the after, and I have 5 in the before as well. So in the whole picture, not necessarily the system, but in the whole picture before and the whole picture after, the total number of particles always need to be equal. Understand that the whole picture is different than the system. Okay? So this is a situation in which particles entered the system. Now, if there's a decrease in mass, that means at the end my system is going to have less particles. An example of this would be the baking soda and vinegar. Another one people struggled with modeling on the Unit 1 Quiz 3. Okay, so I'm going to make my before and after. So before, after. So first of all, I have 2 ingredients. I have baking soda and vinegar. I got to show both of those separately. In the before, maybe I show a couple of containers. And maybe I just make 3 dots of each. I'll make vinegar. Sorry, I'm kind of shortening things. Don't shorten them on a quiz or test. I'm just doing it because I'm running out of room here. But vinegar, I'm going to make be red dot. And I'm going to make the baking soda blue. I don't know why. So maybe I have 3 baking soda dots, particles, and I have 3 vinegar particles, and that's my before. Could have made 4, could have made 5, could have made 100 if I wanted to, but it's always better to stick to a smaller number of particles. That was another issue I noticed from quiz 3 was that sometimes people would make a container and show the particles like this. Like, how many particles are there? Are you showing law of conservation of mass? Because then the one afterwards would be like this. Like, are there less dots? Are there more dots? I don't know how many dots are in each picture. I should be able to tell. Okay? Some people actually labeled the number of dots in each system or picture, and that was helpful. That was nice. So don't put too many. Just use as many as you need to illustrate the point, illustrate the concept. So in the baking soda and vinegar, we combined them. And one thing we should have noticed at this station, sorry, this is all for this. One thing we should have noticed at this station is that it foamed up. There was a lot of gas produced, okay, at the station. So if gas was produced, that means particles left. It also means chemical change. So maybe what I'm going to do in the after picture is combine some of these and show them going into the air. So maybe I show something like this. Now I have, in the before picture, I have 6 total particles. I have 3 red. I have 3 blue. 6 total particles. So I better have 6 at the end too. And if we remember, it wasn't like everything just foamed up and gas produced and everything was gone. There was still some stuff left. So maybe in this after picture, I combine a blue dot and a red dot. Maybe they're not stuck together, okay? But now I have 6 total particles in the before picture and 6 total particles in the after picture. I have 3 reds in the before. I have 3 blues in the or 3 reds in the before, 3 reds in the after, 3 blues in the before, 3 blues in the after. So this shows conservation of mass. All right, so each picture has 6 total particles. But each picture is not the system. The system is just what we're paying attention to in terms of mass. So each system is this, system is this. Okay, so we see in the beginning we had 6 particles, but in the end we only have 2. That indicates a decrease in mass. So understand the difference between the picture and the system. Stay the same, like ice melting. Okay, so here's my before picture. Here's ice. Here's my after picture. The black dots indicate water particles. So this picture, this is the system, 4 particles. In the after picture, this is the system, 4 particles, no change in mass. Good. Another one, sugar dissolving, real quick, sugar dissolving. So sugar, I had 2 ingredients. I had sugar and I had water, and I'm going to combine them into one container. Here's some water. I'm not going to bother making a key. Here's some sugar. I should make a key, though. And then I combined them, but it wasn't a chemical change. Just dissolving water. So at the end, I'm just going to put them, kind of mix them up. And here, I'm not really sticking them together, but so I had a total of 6 particles in the system before. I have a total of 6 particles in the after. Okay, that shows no change in mass. All right, I'll move quicker now. Just wanted to make sure, because that was an area people lost a lot of points on that modeling. So I want to make sure you guys have that down for Monday. What's the difference between an open and closed system? In an open system, particles can enter or exit the system. In a closed system, they can't. Well, they can't. Particles can't. I could write it all out. So that baking soda and vinegar station where we put the baking soda in the vinegar and it foamed up a lot, if I had put a lid on that right away so none of the gas could escape, we should have seen that there was no change in mass instead of a loss in mass because no particles could leave the system. They're still there in that container. What is the equation for a slope? We do rise over run. And really what that means is the rise is the difference in y values, y2 minus y1, and the run is the difference in x values, x2 minus x1. Now in 27, I should have told you this is my fault. But when you see coordinates, if you haven't had this in math already, When you see coordinates, the first one is your x, and your second one is your y. Now, when we do the slope, we take a line and we work left to right, and we're going to have 2 points on it. Okay, so the one that's to the left is our x1, y1, and the one that's to our right is our x2, y2. And this, of course, is the x-axis as we go horizontal, all right? So the one with the higher x value will actually be our x2, and the one with the lower x value will be our x1, all right? And then, so this will be y1, and this will be y2. So if I plug those numbers in, y2 is 37, minus y1 is 11, 37, 11. X2 is 18, minus x1, which is 5. No units given. Normally, I would want to make sure that I include the units for my slope, which would be the y value units over the x value units. But they didn't give any units, so I don't have to worry about it on this. 37 minus 11 is going to be 26. 18 minus 5 will be 13. 26 divided by 13 is 2, and that's your slope. For 28, if we're going left to right, and we hit the line and go uphill, that means it's positive. Left to right, you hit the slope and you go downhill, that's going to be negative. Which one has a negative slope? B. Cool. Yeah. So you actually found the slopes. And did you get a positive number for A and a negative number for B? No? You got -2 for A. So if I pick 2 points on this, what points did you pick on A? 0, 2, and what else? -2, -2, so about here. All right. So my dot to the left is my x1, y1. And then the one that as I go to the right is my x2, y2, right? So my y2 value would be 2. And my y1 value would be -2. All right. And my x2 would be 0. And my x1 would be -2. Do you know what it is when you subtract a negative number? Positive number. Okay, so really the top ends up being 2 plus 2, be 4, and the bottom ends up being 0 plus 2, which would be 2. So it should have a slope of 2, which means as you go to the right, if I go to the right one spot, I should go up 2. That's what it means. Does that make sense now? And then if you do that over here, you should end up getting a negative number. All that math will not be on there. All right. In number 29, given the data below, identify the manipulated and responding variables. You guys know I like to use, instead of responding, I like to use dependent. We do use dry mix, so that should help us remember that the responding, that means dependent, all right? And the reason why I like using these terms is because if I look at the data over there, I've got water depth, I've got temperature. First step, by the way, if I'm going to make a graph, is I got to make a title, which I would just use this title, and I'm trying to go a little quicker here. So I would just write that in: water temperatures versus various depths would be the title of my graph. All right. Now I have water depth in meters. I have temperature in degrees Celsius. So the reason I like to use dependent is because I can say this. I can ask a couple questions. Does the water depth depend on the temperature? Or does the temperature depend on the water depth? Which one makes more sense? Water depth depends on the temperature, or the temperature depends on the water depth? I agree. I would say temperature depends on the water depth. So it's the dependent variable. The dependent variable goes on the y-axis, which is the one that goes up and down. So I'm going to put temperature on that axis. A lot of people still forgetting to include units. Always include the units. You notice I've been marking those off every quiz we've had. My units here are degrees Celsius. And so this axis is going to be water depth. And the units for that are meters. Okay? So I have the y-axis and the x-axis labeled in terms of what they are. Now I got to come up with a scale for each one. So I'm going to start with water depth. I got to look at what's the highest number I have to cover in water depth. The answer to that question is 200. So what I'm going to do is I'm going to take that 200, that highest value I need to get to. I have a pre-made graph right here. I'm going to count. I don't know how well you can see it in the video, but there's these little marks here, and there's 9 of them. Okay, so that means I have to cover 200 units, in this case 200 meters, in 9 marks. So what I'm going to do is I'm just going to divide that. Okay, so 200 divided by 9 means I need to make each mark. I did the calculation last hour, so I know what it is. I think 22.22 or something like that. All right. So that means if I make each mark worth 22.22, I'll get to that last mark and I should be right about 200. The problem is 22.22 is not an easy number to deal with and make sense of when we're looking at the different lines. So I want to make it something that's easier to work with. And in order to do that, we can only round up. So I can round up to 22.5. But again, not that easy to work with. I could round up to 23. Not that easy to work with. 24. 25. I like 25 because 25, I could just make every 4 marks 100 meters. And so I don't use all the marks, but pretty close to all of them. All right. So that's how I get my scale for the x-axis. Now on the y-axis, my highest number I need to cover is 18. So I got to go up to at least 18. So if I do the same thing there, I got to go up to at least 18. And now I think on the y-axis, we actually have more marks to do this. 2, 4, 6, 8, 10, 12, 13 marks to do that. And so if I divide that, I think I get like 1.3 something like that. Okay? Again, not an easy number to work with. I could round it up to 1.5. 1.5 isn't very easy to work with either. But the thing with 1.5 is I can make every 2 marks worth 3. But I don't like that much. I'm just going to continue rounding up. I'm going to make each line worth 2. Is that okay with you guys? So if I go every mark is worth 2, I can just say 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. All right. So there is a part of my graph that's going to be a little extra, but it's not terrible. And I should be able to plot my points fairly easy. Wish these were darker on here. But so my first one is at a depth of 50 meters, the temperature is 18 degrees Celsius. So each one of these are worth 25. So 2 marks would be 50. I'll do these in blue. So that would be 50 right there, 50 meters. And the temperature is 18. So I know I went by 2's on the temperature, so I would make my point right there. That indicates a depth of 50 meters and a temperature of 18 degrees Celsius. If I go one more spot, go to 75, then I'd go to 15. So here's 10, 12, 14, 16. It'll be in between 14 and 16. If I go to 100, it's 12. So that'd be 1 mark above 10. If I go to 150, here's 150, and go up to 5, so 2, 4, 6, right in between 4 and 6. And then 200 would be 4, so here's 200. Go to the second line, which means 4. All right, now when we plot these dots like this, we want to make a best fit line, or at least make a connect the dot line. Kind of curves a little bit. Looks to me like the temperature drops kind of at a steady rate for a while, and then when you get to a certain depth, it's going to kind of flatten out, according to this data. All right, so that's how we do the graphing for number 29. But think about that. Title, there's 2 parts to this. You got to have a label, you got to have the scale. 2 parts to the x-axis, label, scale. And usually I make the graph itself worth 2 or 3 points based on the points and the line that you draw. Okay? So that's that. Number 30, does box A or box B show what would happen to a substance, dark dots, that is soluble in water, light dots? So we got to understand what soluble means. Soluble means it can dissolve. Okay, and what dissolve means, it's a physical change, it's not a chemical change, we're not making anything new. But take, for example, dissolving sugar in water. Okay, it's still sugar. We could tell if you did it at home, if you took some sugar cubes and you dropped them in some water and stirred it and then drank that water, you would taste sweet water, sugar water, all right? So what happens is all these sugar particles kind of arrange together normally. That's what makes up sugar. When we dissolve it in water, all those sugar particles break apart. It's not a chemical change because we're not making something new. It's still sugar. It's just they're not clumped up. That's really what this means. Okay, explain your choice. I would say A is my choice. Substance is being separated into smaller parts. Okay, so that is that. All right, number 31, does the diagram below show an open or closed system? Does it look like particles can enter or exit that system? I agree. It looks like these particles up here, especially, are either leaving or entering, depending on which direction they're going. I would say this is an open system. Particles look like they are leaving, entering, one of the two. Okay? In a closed system, particles can't enter or exit. I put a lid on this thing. Now it's a closed system. All right, number 32, we have these 4 different samples. Asks us to rank the 4 in terms of mass, volume, and density. First of all, what is mass? Amount of matter in an object. And just to make it simpler, amount of particles, because particles are the models. Or I'm sorry, particles are the matter. What's the matter? Particles. That's right. And we just draw those as dots or little red circles on this model. So the one that has the most dots is going to have the most mass. So is there one in there that has more mass than the others? Yeah, they don't all have the same mass. I would say B has the most. So I'm ranking these from largest mass to lowest. You could rank them the other way if you wanted to. But remember the wide side of that less than, greater than symbol, the wider side of it goes towards the bigger thing. All right, what would come next in terms of mass? Okay, so B has a greater mass than A, and A has a greater mass than C. That's got 6 dots, and D has the least. What about volume? What is volume? Amount of space an object takes up. So you think of kind of like the size. Did they all look the same size, or do we have different volumes? They have different volumes, you think? If they have different volumes, it's pretty hard to tell from this. I'm just going to say they're all the same. So I would say A is equal to B, which is also equal to C, which is also equal to D. Now here's the thing. So if you remember that density equation, density equals mass over volume. The things on the top of the equation have a direct relationship. So that means if the volumes are the same and I increase the mass, the density is going to go up. The thing, if I have the opposite relationship like I have between density and volume here, the opposite will happen. If the mass stayed the same, but I increase the amount of space available to the particles, the density would actually go down. So if I increase the volume, the density would actually decrease. Another way of knowing just by looking at models, if you weren't sure from this, is just looking at the particles themselves, because density is really like saying how compact or how tightly packed the particles are. So if I look at those, does it look like one of the pictures have particles that are closer together than the others? B looks kind of bunched up. So I'd say that's the most dense. It would be exactly like the first one because, again, we're not changing the volume. They all have the same volume, but what we're changing is the mass. And so if the volume stays the same, but we increase the mass, that means direct relationship with density. So it's going to be the same as number 1. And it should look like that in the picture. Doesn't it look like B, the particles are closer together than A, and A, the particles are closer together than C, and in C, the particles are closer together than D slightly? All right. So that's that. All right, 33. So we're going to use that that pyramid, whatever, mass, density, volume. We're given 3 densities here for gasoline, magnesium, and silver. We got to be able to, this is very, very important. I can't stress it enough, guys, that you have to be able to look at the units and know what kind of measurement they're talking about. You have to be able to see cubic centimeters and go, oh, that's a volume. You have to be able to look at grams and say, oh, that's the mass. You need to be able to see grams per milliliter or grams per cubic centimeter and go, oh, that's density. Just got to memorize it, okay? So in 33, they tell me the volume. And I also know we're talking about magnesium, so I know its density is this, all right? So they want me to find the mass. So the way I use this chart is cross out the thing you're trying to find. That leaves me with density and volume, which are next to each other. That indicates multiplying them. So I'm going to take the density and multiply by the volume. So the density is 1.74 grams per cubic centimeter, and times the volume, which is 30.0 cubic centimeters. Does anybody have an answer for me? 2.2? 52.2? Okay, what are the units? Grams. All right. 34, you have 7.5 grams of gasoline. So again, we know that that's the mass. We know the mass. They want us to find the volume. So just to do this real quick, mass, density, volume. So this time they're asking me to find volume, which means I'm going to have mass over density. So mass on top of density, mass divided by density. So, well, first of all, I would do 7.5 grams divided by the density of gasoline, which is this, is 0.69 grams per cubic centimeter. And what'd you get? 5.175. You guys all agree? Is that right? 7.5 divided by 0.69? 10.86. Yeah, okay. So, and actually with this just using two numbers, I could round that off to 11. Or you could put 10.9 or whatever you want to put. Now, what are the units per volume going to be according to this equation? Okay. So yeah, if you look at the equation, in the equation I have grams, got grams again, got cubic centimeters. It's going to be in cubic centimeters. How would I change that to milliliters? It'd still be 11, right? 11 milliliters, because 1 milliliter is equal to 1 cubic centimeter. All right, if you put gasoline in water, would it sink or float? Float. Why? Less dense than water, because we should know that water has that nice, easy 1 gram per milliliter or cubic centimeter, whatever you want to say. All right, it's just density of water is 1. Number 36 was kind of a tricky question. We're talking about silver in all of them. Okay, so remember that density is a characteristic property. So no matter how much I have of silver, the particles are still going to have the same arrangement in the silver. So if I have 6 cubic centimeters of silver, it's still going to be 10.5 grams per cubic centimeter. If I had 15 cubic centimeters of silver, I would have more. Okay, I'd have more mass, I would have more volume, but it's still silver. It would still be 10.5 grams per cubic centimeter. If I had 100 cubic centimeters of silver, I would have more silver. But the density would still be 10.5 grams per cubic centimeter. Because all this is, density is a comparison between the mass and the volume. So although the volumes are increasing, so is the mass. And it's going to be staying, the density is going to be staying the same at the same rate, which would be the slope of that line if I plotted those masses and volumes. And that slope would be 10.5 grams per cubic centimeter. 37, why does that make sense? 0, 0. Okay, the origin. In this case, graphing mass and volume, if something has 0 for its volume, takes up 0 amount of space, then it should also have 0 mass, right? Basically, it's referring to nothing. If you have nothing, it's going to have 0 volume, 0 mass. And then people are getting to this point, and they're like, oh, almost done. Now I got to make a graph of 3 different lines. I know how graphing goes. It takes forever. But not this one, because it's just a rough graph. And we should know the greater the density, the steeper the slope. So all I got to do is make my outline of a graph. I'm going to make 3 lines. I'm going to make one that's kind of flat. That means it has a small slope, a lower density. That would be the gasoline. Make one a little bigger, steeper slope. That's going to be my magnesium. And even steeper slope, maybe something like that, silver. And you should be able to go the other way around. I should be able to just give you a graph like that and say which one has the highest density, and you should be able to say silver. Which one has the lowest density? The one with the lowest slope, the smallest slope. The flattest one, gasoline. Don't forget to have this in your calendar for Sunday or whenever you're going to study. Set an alert. And that's it.